So in our previous chapter, we finished on the molecular model, which explained more about the states of matter very briefly. So now in chapter 14, we're going to continue on with that, with going for more models of matter. So the one thing that the molecular model didn't really explain was this thing that they found in the gas discharge tube experiment. With the gas discharge tube, what they did, they filled a tube full of gas, and they sent an electrical current through it. And when they did that, positive charge was separated and went on one end, and the negative charge was also separated and it ended up on the other. With the positive charge, it had most of the mass with it. It was very equal to the original gas, while the negative charge was negligible, just nothing there really. So the molecular model didn't explain the charges. J.J. Thomson used this to create the next model, which is the Plum pudding model. Plum pudding model, instead of thinking like plum pudding, think of it more like a chocolate chip cookie because no one eats plum pudding. The dough is all the positive charge, just spread out all over the place, while the chocolate chips are the electrons, just sprinkled in there. And this is what J.J. Thomson came up with. It explained the charges, it gave us our little tiny particles, they can be moving constantly, it helps explain everything else. So the next thing that they did, Rutherford, he was actually trying to prove this model. He did this thing called the gold foil experiment. And what he did, he took a piece of gold foil and hammered it down very, very thin. Gold is very malleable, so you can have it just be a couple molecules thick. So he had this gold foil here, and he shot alpha particles through it with a little gun. Alpha particles are positively charged particles, remember that. And he would shoot them through this, and he had a detector on the other side, and he was expecting it to come through and hit the other side on the detector because that the positive charge in the molecule is so thinly spread out that even though this is a positive charge as well, it will not repel it at all. It will just go straight on through. So this was happening for a long time and everything was going well, and then they decided to set up a detector in the back. Or when they did that, they found that one hit the gold foil and bounced all the way back here and hit the one behind the gun. This to them was like shooting a bullet at a piece of tissue paper and it bounced back. It was not supposed to happen at all. So what they discovered with this was that instead of the positive charge with the plum pudding model being all throughout it like this, they determined that it has to be all concentrated in one nucleus. That would allow it to have a dense enough concentration of charge for the alpha particle to hit it and bounce back. And the electrons would be orbiting around the nucleus. Another reason why it missed it so many times is that the nucleus in comparison to the rest of the atom is so tiny. It's like putting a dime in the middle of a football stadium. So it had a lot of empty space for those alpha particles to go by and miss it. With that, they came up with this model that I just drew, which is the solar system model. Some people like to think of it as the Jimmy Neutron, because that's what it looks like. This one is exactly like I just explained. You have your positive nucleus with the electrons orbiting. The problem with this one, though, was that it couldn't explain this observation we had called discrete spectra. Discrete spectra is like the fingerprint of an element. You've seen this in class before with those tubes, and they send the electrical current through it, and then you have that diffraction grating that you hold up to your eye, and then you can see all the different colors. And each one has its own specific lines that it shows. What would happen if this one was correct would be we would see a continuous spectra because these electrons are constantly orbiting any energy level they want to. And if they were doing that, they can give off any amount of energy, any and all colors. And since we don't see that, we see specific lines with certain elements, we know that there has to be energy levels involved with this. So, a guy by the name of Bohr came up with a modified solar system model, We have our nucleus in the middle, and we now have energy levels on the outside. The lines closest to the nucleus are the lowest energy levels, and the ones on the outside are the highest. So we have an electron that's orbiting around on the lowest energy level. If it wants to go all the way out here to this one, it has to gain energy, so it's going to absorb energy into it. It's actually going to absorb a certain color. It's going to absorb energy in a photon. So if it has to make a huge jump, it's going to be high energy, and so that's going to be more purple in color. If it was going to make a jump small like that, only to there, it's going to absorb a reddish color, something on the lower end. And then the very same thing happens opposite if it's going from a high energy to a low energy. So if we're going from high to low, it's going to have to release energy in order for it to be in the lowest one. So when it makes a big jump, it's going to show a violet color. When it makes a smaller jump, it's going to show a red color. So still, there was a problem with this model. The problem was that these electrons are still orbiting. They cannot orbit at all. If they were orbiting, they would continually be accelerating, and they would be releasing energy, and they would slowly just crash into the nucleus, and everything would collapse. And we know that can't happen because everything is still here. We're all made of atoms. We're here and alive. And so that's why we can't have this one. Our next model is called the quantum model, and we'll get to that one in the next couple of chapters.